So we're going to work through all three types of gas stoichiometry problems. Remember a couple of things about gas stoichiometry. Oops, gas stoichiometry. That gases at STP. What does STP mean? Unmute yourself and answer my question, please.
Standard temperature and pressure.
Standard temperature and pressure. And the units for standard temperature and pressure are what, Ethan?
Temperature is Kelvin and pressure is ATM. 1
Okay.
ATM.
And what is the value? 0.
1 ATM and 273 Kelvin.
Right. Usually we say 0 degrees Celsius, but that's equivalent to 273 Kelvin. So just keep that in mind. But also at STP, what is molar volume of a gas? Jacob Boling?
22.4.
Yeah, 22.4 liters in a mole. So sometimes that will simplify our processes. So let's take a look at the first problem. The mole volume stoichiometry, you're going to be given moles of one component. You need to find the volume of another gaseous component. And the temperature and pressure have to be stated in a problem such as this. So you can use these steps. You convert the given moles to the needed moles using the coefficients of the balanced equation, because we're doing stoichiometry, so it's not going to be any different. We want to get to the mole-to-mole ratio. So given moles to needed moles, then convert the moles of the needed volume to using the ideal gas law. So here we're marrying our process of stoichiometry to the ideal gas law. So we're going to be flipping back and forth between processes to some degree in these problems. So here's a mole volume stoichiometry example. Given the Haber process, which is the process of producing ammonia gas, just taking the elements nitrogen and hydrogen and producing ammonia, you are going to have to calculate how many liters of ammonia can be produced at a temperature of 27 degrees Celsius and a pressure of 760 torr if 20 moles of nitrogen are consumed. So, starting with the given number of moles, we have 20 moles of nitrogen. And we need to figure out the needed moles. So here we're going to use the coefficients in the balanced equation. This is basically the mole ratio. Okay, the mole ratio. So we're going from nitrogen to ammonia. So nitrogen to ammonia. So it's 1 mole of nitrogen to 2 moles of ammonia. That tells me how many moles of ammonia I'm going to make. So this would be 40 moles of ammonia. Now the second part of this is we have to deal with the ideal gas law. Notice 27 degrees Celsius, 760 torr. This number, 760 torr, what is the equivalent in atmospheres? Carter. Yes, I see your lips moving. 1 ATM. 1 ATM. Okay, so we have 1 ATM. That would be our pressure. So that's satisfied by the STP values, right? That's equivalent. So look at the temperature. It's 27 degrees Celsius, which we add 273. That's 300 degrees Kelvin. So it doesn't satisfy our STP. So we have to then use PV equals nRT to calculate our volume. So we have N, that's 40 moles. We have R, because we know it, it's 0.0821 liter atmosphere per Kelvin mole. P is 1 atmosphere. V, we don't know. N is 40. 300 is temperature, and then 0.0821. So I want you to get your calculator out and calculate that. Right, 985.2 is correct, and the unit would be liters.
I have a question.
Okay,
Do we not use sig figs?
sig figs. You should always practice sig figs. So in this case, it would be 990 liters of,
Wait, isn't 20 moles 1?
oh, you're right.
9.
So it'd be
1,000.
1,000 liters. That would be appropriate sig figs. It's always good practice. I am not grading on sig figs, but you should always practice using them. Okay. So that's that one. Let's look at the next one. You guys try it on your own and then we'll work it together. Jaylee, where did you start?
I started with converting 2 moles of KClO3 to O2.
To O2, correct. And how did you do that?
Well, I went from 1 mole of it to 3 moles of O2, which is 6 moles of O2.
Actually, look at the balanced equation. It's 2 moles of KClO3.
Okay.
So down here you need a 2,
Okay.
and then it ends up being 3.
Okay.
All right, good. Lauren, what do we do next? Drum, sorry.
Then we take it and we plug it into the one equation, the PV equals nRT.
Correct. So here we have pressure and torr. We don't like that. So the first thing you're gonna have to do is convert this to ATM. So 760 to 1 ATM.
It's 2 ATM flat.
2. That's nice. Okay, so pressure is 2 atmospheres. Volume is what we're looking for. N we just calculated as 3. R is 0.0821. T, 37 degrees. So 37 plus 273,
310.
310. And then we can calculate the volume.
I have the answer when we're ready. It's
Okay, tell
are
me.
we ready?
Yep.
38.18, or I don't know what sig figs is. It's
Well, we have 2 moles. So
Yeah, we have 2 moles here, so it's 1 significant figure. So you're right, Noah.
40.
40.
And then it's 40 insignificant figures. All right, so that just demonstrates to you that when you're not in standard conditions, 1 atmosphere, 0 degrees Celsius, you have to use PV equals nRT to get part of your answer. You can't just do straight stoichiometry and use mole conversion because it doesn't work for gases. So let's look at the second page. it says up here, if you are given the volume of gaseous component, asked to find the number of moles involved, then you would simply reverse the 2 steps above. Okay, so you would first use the PV equals nRT to convert volume to moles, and then convert moles of the gas to the other component. So you can do this backwards to our process too. And that would be going from volume to moles, in which case you would use PV equals nRT to find the moles of the gas, then find the moles of the other substance you're looking for. Okay, so here is another one, mass to volume. So here we have three different steps. You're going to convert the mass to moles, then you're going to use the mole ratio, then you're going to use PV equals nRT. So it's just an additional step because you have to get the given mass to moles. So here, same Haber process. Here's the balanced equation. How many liters of hydrogen? So we're looking for some number of liters will be required at a temperature of 300 Kelvin, 3 atmospheres. Again, not standard conditions. And then 56 grams of N2. So we know the grams of N2. Notice these are on the same side of the equation. But we can remember stoichiometry, we can figure out any number of, or any combination of elements if they're on the same side, or if they're on opposite sides. We can go backwards, we can go forwards. So 56 grams of nitrogen is our starting point, because we have to first get this to the moles of nitrogen so that we can then get to the moles of the hydrogen. So 28 grams in a mole of nitrogen. And then the mole ratio, our second step, it comes from the balanced equation. So 1 mole of nitrogen to 3 moles of hydrogen. Here's where we stop, because we want to use the moles of hydrogen in PV equals nRT, okay? Because we can't get to volume of hydrogen here because it doesn't satisfy the 0 degrees Celsius 1 atmosphere conditions of the 22.4 liter conversion that we know. So we have to stop here and we get some value. Somebody do it for me because I don't have it.
It was 1.5.
4.5?
I got 6.
I mean 6.
I got
6.
6.
Okay.
Divided into multiply.
Okay.
This is Keys.
Yeah.
I accidentally brought an Apple Pencil instead of a real pencil. Can I go get one?
Yes, you may. 6 moles of hydrogen.
Weird flex, but okay.
So we have satisfied steps 1 and 2 here. So now we're ready to go to PV equals nRT. So we know pressure, here it is. We know volume, or we're looking for volume. We know temperature. We know R, because that's always constant.
Conveniently.
And now we know N, because we calculated it. So plug and chug. So P is 3, V equals 6 times 0.0821
It's funky looking, isn't it?
times 300K. So calculate that. You can shout out the answer when you have it.
Is it 49.26?
Yes. And then if we went to sig figs, it's based on this 3 atmospheres. So we have to go to 1 sig fig, which would be 50 liters of hydrogen. So good job. Try example 4 on your own. Noah Hastert, where shall we begin here? Don't forget to unmute yourself so I can hear you.
You have to convert KClO3 in grams to moles.
Okay, did you figure out the molar mass of that?
No, I've not figured that out.
Let me just tell you.
What is it?
It is, I got it to be 123 grams.
123.
Did anyone else look?
Yeah, that's what I got.
Okay. 120.
Then I got
Okay.
General assent.
Okay, so then the next step is mole to mole. So it's 2 to 3. So 2 moles of KClO3. Give me
Is
an.
it 4.4?
Yep, it is 4.485 moles of KClO3.
No. Oxygen.
Oops.
You missed.
You guys didn't correct my work here. You're not paying attention to me, but that's okay. You're not supposed to be. You're supposed to be doing your own work. Okay. From here, Leah, what do I do?
You put all the stuff. Wait, never mind. You have to figure out the other variables, like the others. I don't know.
So, yeah, so you're assigning PV equals nRT. Is that what you mean?
Yeah.
Right. Yep, you're right. So temperature is here. It's 27, but that's 300 K. You have volume, which you're looking for. You have R, which you always know as long as your pressures are in atmospheres. So now we can plug in chug. 1 V 0.0821 in 4 point, I'm doing this out of order, sorry. And T 300.
I got 110.465,
Okay,
which
5.
110.5.
Well, we have 1 ATM.
all right. So there we go. Hopefully you were able to get 100 liters. All right, any other or any questions on this one? You kind of see the process. Volume to volume is last but not least, and these are the easiest because of the law of combining gas volumes, which says that gases combine at the same temperature and pressure in simple whole number of volumes. What this means is that you can use the coefficients in the balanced equation to form volume relationships, just as we did in earlier problems when we use the coefficients to form mole relationships. So basically what we're saying is this is 2 moles to 1 mole to 2 moles. But you can also call this 2 liters, 1 liter, 2 liters.
But 1 mole of oxygen is not 1 liter.
Right, but it proportionally, you're going to end up with these ratios. How many liters of water vapor can be produced if 40 liters is consumed in the above chemical reaction? All gases at the same temperature and pressure. That's a key phrase right there to do this. So if I have 40 liters of hydrogen, how many liters of water do I get? 40. How many liters of oxygen would I have? 20. So that's how you interpret volume to volume problems if they're all at the same temperature and pressure. So down here at the bottom, 10 liters of nitrogen. How many liters of NH3? And you say what? At STP, don't forget that it's simply 22.4 liters in a mole. So you can use straight stoichiometry if it's at standard temperature and pressure. And this can be your conversion to volume, okay? So I didn't do those kind of problems because we kind of handled them in stoichiometry, but it only happens at STP. Every other situation, you're gonna have to marry our stoichiometric process to the PV equals nRT process.